Anyways, before we get into hashing itself, I thought I would motivate why somebody would be curious about exploring the concept of hashing. So, at least from a data structures perspective, one way you can go about this is perceiving or realizing the issue of, say, a dictionary. So what is called a dictionary in data structures. Sometimes this is also called a map. And the idea is as follows, that the dictionary or map contains records. So it contains records. So this is mostly just a reminder. And each one of them, these records are a pair, each with a key. And the second part is its value or data. So the big point in a dictionary is that the keys are unique. There cannot be a duplicate key. So just keep this in mind. So each one of these records might represent all sorts of different things. So one simple application of a dictionary or map, you can think of something like a database, a simple database. Say this is student records. Say each one of the keys is a student ID, and the value or data may be some pointer or maybe a reference or even just some data attribute associated, or it's multiple attributes for that student's information. Likewise, as the name suggests, you can also think of this just like a dictionary. Like each key is a word in that dictionary, and the value or data, maybe it's definitions or multiple definitions. So there's a lot of ways you can go about thinking about dictionaries or maps. There's special kinds of maps as well. For example, there's a so-called ordered dictionary or ordered map. This is where the keys have a special property where they maintain what is called a total ordering. This means that you can take those keys, you can lay them out from smallest to largest. That's an important detail about that. So this may come up at some point here today, but my main point is that very often in data structures, a very common what we call abstract data type is the dictionary. So whole idea here is that it has a bunch of operations. So often if you want to get data from a record, you may also want to, say, insert data into a dictionary. So say the get operation, you give me a key, I give you back the data. I may want to insert a record into the dictionary. Remember, it has to have unique keys, so that's going to be an important constraint on what a dictionary is. And likewise, we may want to remove data from the dictionary. So I give you a key, and I want to remove the dictionary record that has that given key. Remember, they're unique, so there's only one of them at most. So keep in mind that if it doesn't exist, then we don't have anything to remove. So just keep in mind that these are some things you can do with a dictionary. Now, I thought of so there's a couple basic ways you can go about implementing a dictionary. So one common way, common but not necessarily effective for very large sized dictionaries. So this would be something if you want to really whip together something small and would be simple enough, but it has its pros and cons. Say if we have an array. So suppose you have an array, and you have your dictionary. Now, you can maintain this array, or sometimes if you can formalize this further as a list, for example, it could be unsorted or sorted by potentially by the key. Now, if the keys aren't necessarily maintaining a total ordering, it may just be unsorted. So the idea would be that you just simply insert your records into the array from left to right, but every single time you do this, you have to make sure you check to make sure you aren't putting in a duplicate key. So the pros of this approach is it's very simple, but keep in mind that doing a get operation, if it's unsorted, is going to require you, in the worst case, to traverse through this entire array. So suppose you have a bunch of records in here, and I'm looking for one with a specific key. If it's unsorted, meaning that, and this is something that you have to keep in mind, because some of these times the keys don't maintain a total ordering. It may be just that they just have no inherent ordering to them. In many scenarios you actually do, but I must stress that you may have to go through all of the records to check for it in the worst case. So that takes linear time. Inserting, you find a spot, but you have to check for a duplicate key, so you have to scan through anyways. Another possibility you may have with an array is the array may get full, right? So if the array becomes full, you're going to have to resize it by doubling its size or say resizing it in some way. Now, I'm not going to focus much on the discussion about how you do that here, but the point is that you can do insertions, and for removals, you can give me a key. I can search through here to find it. Now, naturally, it may not even exist in here, requiring me to go through all of them, right? So in these cases, each one of these, it could take linear time. It could take big O of n time. Now, if there is the ability to sort the array, say by key, you can improve the get operation to big O of log n. Does anyone have any ideas of how I can do that? If all these keys were, say, numbers instead, like say it's like, say, I don't know, 1, 5, 7, 8, and say I knew how many elements I had in the dictionary. If they're all sorted like this, if you think about it carefully, you actually have all the information you need to perform binary search. In this case, you can actually improve this get operation to big O of log n. Now you might say, Dan, can you do the same thing with put and remove? Unfortunately, the answer is no, because of the same kind of scenarios we talked about here. You may still have to, anyways, deal with a couple things. So first, for put, you may have it where you have to resize the whole array. Now, if that doesn't happen regardless, what happens if you have to do the insertion right at the beginning? Well, you have to shuffle all of these elements over, because you can't just have gaps sitting anywhere in here, right? It has to be that this is all one contiguous entity, right? Likewise, with remove, the same idea, but in reverse. So if I remove, say, 5, I'm going to have to move 7 and 8 over, so everything could stay together. So that's how you could do it with an array, right? So there's pros and cons. So the main pro is it's very simple to implement. However, the drawback is that you're going to have to bite the bullet of have to potentially search through this entire array. You can improve upon this a bit further if you know that the array can be sorted based on the keys. Now, another way you can go about this is using a linked list, and it has the same kind of predicament or quinky dinks. So in this case, you may have it where you have a linked list, or maybe even be a doubly linked list. That's where you have pointers or references that go from to the next node, but also to the previous. But there's a lot of ways you can set those up. So in a linked list, for example, I may have these same records. Now keep in mind, remember, these are keys I have here. So there may be some data associated with them. You're going to find very often that the data or values aren't going to be very relevant for the discussion here. It's the keys that really matter, because that's the main constraint we have. So if I have 1, 5, 7, 8, if I have these in my linked list, now keep in mind there's going to be data associated with each one of the records. These are just the keys. Notice they're going to have the same issue as well here, because you're going to still have to have it where you get, and you see, hey, look, if I try to get one for a given key, notice that if it's sorted, I know when to stop, but I may have to go all the way to the end, right? Likewise, for an insertion, what happens if I have to insert way at the end? Like, say if I insert 10 in. If I need to put 10 in for some record that has a key value 10, then it's going to have to go way here at the end, which that's a problem, right? Because you're going to have to go through the entire linked list. So you see that we're not really getting anything beneficial beyond kind of the scope here. So the pros and cons are quite evident here, is that there's some elements that where we can improve upon things. And one thing I want to point out or emphasize is, what if I could take this linked list approach? Because a lot of the facets, if we had to have an unsorted array, are redeemed by the linked list, because now I don't have to worry about resizing. I just have these extra pointers I use to make just a new node, and I put it at the appropriate spot, right? However, what if there was a way that I can have it so that when I do like get, put, remove, that this can be shorter? Because we know that if ever I had to do an insertion or I wanted to search, it works rather well when it's right at the beginning, right? That seems to be the best case scenario, right? In this case with the linked list. Does everybody see that? So if I were, for example, retrieving 1, I would start, like, say if you have a head pointer, which is what you would have in the linked list, you'd point it right at the first node here. If I can get 1, so if I try to use that key 1, I'll get the first one, right? I don't have to go through all of these. That's a best case scenario, right? It's always at the beginning. Likewise for insertions and removals, if they happen at the very beginning of the linked list, that's wonderful, right? But here's the thing. Here's the kind of the catch, is that 1, we still, if ever I do insertions, I still have to go through here to check to make sure there isn't a duplicate key, right? And likewise, it may be the case that I actually have to go through all of these. But is there a way I can try to make this so that the linked list isn't too long? Is there a way I can combine this idea, where I am able to directly access given spot, with this idea of trying to make the linked list shorter? And that's, you're going to see that both of these elements are going to pop up in our discussion about hashing. Hopefully that's clear. So if I could make it, say for example, that whenever I try to do access at a given spot, I don't have to do much of this, what we call hopping. I don't have to hop from node to node, or I need to hop from one slot or position in this array to another one. I would like to reduce that from happening. So you're going to notice that both these facets are going to be critical in hashing. And I'm hoping that these two ways you can implement a dictionary will help motivate. Now keep in mind, this isn't the only way you can look at a hash table, but most certainly this will hopefully give you a couple ideas of where we're going with this. So let's talk about hashing now with that in mind. So again, if you have any questions, don't hesitate to stop me. Type it in the chat, and I'm really happy to answer it. So anyways, let's talk about hashing. So previously I introduced a bit about dictionaries and a couple ways you could implement them. I give very high level descriptions for how you can do it, right? So here's one thing that we can try doing. We're going to try to use space to help us try to achieve what we talked about just a moment ago. We're trying to make it so we can contract the amount of hops that I need to do. I want to bring that down by trying to distribute that work by using additional space. So we can use additional space along with the concept of hashing, which we're now going to talk about. Hashing to improve on issues we encountered for simple implementations of a dictionary. So in this case, I would like to reduce the complexity of performing our dictionary-based operations. I would like to bring those down. Now, ultimately, at the end of the day, the techniques I'm going to give you here won't necessarily achieve this in the worst case, but in the average case, they most certainly will. But it requires some more assumptions based on the concept of hashing. So let me give you a big picture look at what we're going to talk about here. So suppose that I have, you can think of this just as an array, which I'll refer to as a hash table, and each one of the positions as a slot sometimes. So we're going to assume that this array or table has size capital M, and for the sake of simplicity in our discussion, I'm going to assume it's at least lowercase n, where lowercase n represents the number of elements that will be in the hash table. So the number of records. So suppose I have 0, 1, 2, So you have a bunch of these slots in this table. So since there's m slots, there's indexes from 0 all the way to m minus 1. So this is our hash table. So this is what a hash table would look like. Very often you'll see it draw me vertically like this because it's like a table, right? Very often tables, we don't draw them sideways, horizontally. Often they're drawn vertically, but they don't have to be. It's just a matter of preference here. So suppose I have a bunch of records. So each one, say if I have a first one with a key K1, a value V1. Say it has a second record, K2, with a value V2, K3. So a third record with key K3 and value V3, all the way up to an nth record with key Kn and value Vn. And I would like to be able to put them into this hash table. So here, let's think about this. So you might first say, Dan, one issue that we had, now you got to remember, these keys do not have a total ordering. They may not necessarily have that. So you have to keep this in the back of your mind when we think about this. So when we had our unsorted array implementation, we would have just stuck that one in the first spot, that into the second spot, this into the third spot, and so on, right? So what I would like to do is I would like to try to make it so that there is some way I can easily access where exactly this guy is, so that if I were to know its key, I can access where it is. And if I'm able to achieve this without any weird issues, I should be able to instantaneously access that record. Likewise, if there's nothing in a slot, then most certainly I could do the insertion right away. This brings me to the idea of a hash function. So suppose I have this thing I'm going to call h, and it takes as input a key. So this will be what we call the hash function. And I would like to think of the hash function as something being easy and fast for me to compute. So in practical settings, it would be ideal that this takes big O of 1 time, meaning it takes constant time, or like in this case, very often it will be that the key always has a fixed or constant length, but as I'll talk about later, it doesn't have to be. It doesn't have to be. It's just that if you have it where the key has a constant length, many techniques are fairly easy to apply to make it so it runs in big O of 1. So suppose I have my get, put, and remove operations. So suppose it takes in a key, put takes in a key and a value, and say remove takes in a key as input for its parameters. So each one of these, what I would like to have happen is whenever I do one of these operations, I'm able to give this key to the hash function, and it should be able to tell me where in the table it's located. So it should be able to tell me this. So you could look at it as a lookup. So you may have heard of the phrase lookup table. This is one way you can look at it, pun intended. So suppose that I took each one of these records, I took each one of their keys, I use that, and it tells me a position in the table. I would like to be able to have it so that, say wherever there isn't an occupied spot, suppose that this is nil or null, whatever it might be. And suppose, say, slot or position 2 has K1 in it. Suppose slot 1 has K3 in it. And suppose this one has Kn in it. And suppose the very last slot has K2 in it. So what I would like to have happen is that you should be able to, when I produce a put operation on each one of these records, they give me a position to insert it into the table. As I am going to talk about, it's not as necessarily as simple as this, but most certainly this is the big idea, is that when I put in K1, it tells me a position. In this case, it'll tell me tells me number 2. So it tells me 2. And then I can insert K1 V1 in slot 2. Likewise, with K2, I should be able to use K2, and it tells me K2 should, the record with K2 should go into position M-1, and so on. So you'll notice that this hash function gives me the ability to know where the record is. That's the trick. So notice I don't have to traverse through all of the elements in this very fortunate scenario. But as we're going to see, it's a little bit more complex than just this. So the big idea is you give me one of these keys, I'm able to tell you where it is in the table. And if you wanted to find it, or you want to insert it into that spot or remove at that spot, this hash function will tell you where to go. And if we can have it where we can just do this instantaneously, because this takes big O of 1 time, then that's constant time, then most certainly doing any of these operations should take big O of 1 time, right? But as we're going to see, it's not going to be that simple, unfortunately, at least with some of the techniques we're going to see here. But I will tell you the good news, though. With all three of these, we can achieve big O of 1 time, or constant time, average case. So this is under specific technical assumptions. So I'll talk about those in a little bit. But hopefully you understand the main idea of the whole setup for hashing. So we're going to have a hash table. It's going to store the records. But the thing is, it's going to be that potentially the size of this table may be much bigger than the number of elements. So even the size of the table may be something that's rather important to consider. But also, it may be the case that we may need to eventually resize the tables, meaning that you would have to go through each one of our records in this table and do what we call rehash the table. That means that you're going to have to go through each one of the records. You're going to have to take it, put it into a larger hash table or longer hash table, and you're going to have to rehash it using your hash function. So I thought I'll give you an example of how you might encounter something like this, just to kind of recap everything. So bring it back to one of the applications I told you about. So say if you have a simple database, or just a database, I mean the framework for a map is quite natural for a database, because of the concept of like a primary key is the same as a key here. H must give a position for every ID or identifier. So just to come back to our application, so just as an example, suppose that we considered all the student IDs. So let's consider student IDs at some school. And suppose that has digits. Suppose for our sake of our discussion here, though it can easily be any other number of digits, each with digits. Suppose it's D8, D7, D6, all the way down to D1, D0. So just as an example of what I mean by this, suppose that these are digits and the numbers are 0 through 9. So you could put a 0 or 1 or 2 or 3 all the way up to or 9. So just as an example here, suppose you have a student number like this. Let's see, we have 4, 5, 6, 7, 8, and 9, right? We have 9 digits here, just like I have here. So that would be an example of one such student ID. So you might ask, okay, how would this work? So let's put this back into frame of our hash table. Whoops, I was about to put that there. Suppose that we have 10,001 slots. 10,001 slots. So I have a whole bunch of slots in my hash table. And suppose I give you this ID. Say, we'll call it ID1. And I have my hash function, just like we talked about before. Suppose that it takes in an ID as input, and it gives me a position. Suppose that it says, hey, look, I'm going to put this in this slot right here. So ID1 with its respected value would go right here. Now, there's a bit of a conundrum here. Now, suppose that there are many more student IDs than there are slots in the table, just as an example. So if I have more possible slots, actually no, less slots than there are student IDs, because if you think about all the possible number of these there are, so just remember, if you take the form of this, each digit can take on 10 possible values, right? So if you think back to how you might count this, so each digit is separate from the next, right? So that means that if I look at my first digit, it has no relationship with the second digit. So, and the second digit has nothing to do with the third digit. They're all independent of each other. So if I wanted to know exactly how many possible student IDs there could be, if you think about it, suppose I give you, suppose you had only two, let's say one digit for the ID. You would agree with me that there's 10 possible student IDs if there was just a single digit. If there are two digits, notice that if I have 10 possible and 1, then for each one of those, I could pick one of the possible values, right? So for each one of those, there's 10 of them, I could pick 10 more. So notice that that's 10 squared, that's 100 more possible, right? So notice that I could keep doing this, right? So if you look at this, this means that if I have 9 digits, so there are 10 to the 9 possible IDs, right? This is much, much more than the number of slots in this table, right? Like it's magnitudes more, so many more. So keeping that in mind, we have to be considerate of this when we think about the hash table, because this also opens up an opportunity for the following scenario. Suppose that there's another ID. And keep in mind that this can happen regardless if the number of keys was, say, different than, say, the number of possible keys was less than the size of the table. This can still conceivably happen with the hash function. I'm just trying to emphasize here that this is very much going to be a possibility if there's definitely more possible values than there are slots. Suppose I give you another ID, say ID 2, and because there can be more of these than there are of those, you can guarantee that there's going to be a possibility of the hash function telling you to put it right here. That's a possibility. In hashing, we call this a collision. So that's what's called a collision. So this is a collision. So what we would colloquially call it hashes to the same spot or same slot. So if it does this, we call that a collision. This is going to be a big problem for hashing that we're going to have to resolve. So does everybody understand the concept here of a collision? Is that we need to make sure, if you see that the function plays a really big role in this. Likewise, there's other considerations we're going to have. So just as an example, let me give you some key design issues that you're going to have for hashing. So we've already encountered at least one. So we have this issue when it comes to the concept of a collision, because that will absolutely pop a bubble in the idea that we can, if a collision can happen, one, how do we resolve that? Like, what do you do with that? That doesn't, like, can you just toss out the old record? Well, that's going to be a problem, right? Because we're presuming that record already exists in the dictionary, right? So, like, that's going to be a big problem. So where do we go from here? So I want to talk about some design issues that we have with hashing. So you're going to see that as we explore this topic, all of these are going to be highly relevant. So the first one I will mention is the size of the table. You've seen in our scenario over here that I had way more student IDs than I had for the table slots, right? Now, it's inevitable that a collision is going to happen. if I presume all of these student IDs are used. So you have to keep in mind, you might say, Dan, why don't you just make the table occupy like all the possible IDs? Well, there's sort of an issue with that, is that one, that's a lot of space you're using. So you have to consider this more of a trade-off business, is that there may be some IDs that are used, other ones aren't. So this is more of a design issue that comes back to the size of the table. Likewise, some thing we also have to consider is, what is an ideal size? Like that's generally the question that we would want to answer when about the size of the table. So depending on what you do with your hash function, this can make or break or help your performance considerably. So naturally, you've seen that this hash function, which we have not defined yet, plays a big role. It's the selection of the hash function. It seems to play a really big role in this. So it should be, of course, and keep in mind it doesn't have to, but it most certainly would be nice if it's efficient to compute. So example, it takes big O of 1 in worst case time. So that would be nice if it can do that. So it's efficient to compute. But also, there's couple other things. It causes few collisions. So we would like a hash function that causes few collisions. Now, what that means isn't quite grounded yet. And even then, in practice, a few can mean anything from 8, 9, 12. It might be something like that. It depends on how much data you're processing. That's another aspect of this. So how many records your dictionary might have may have a relationship with this. But the point is we do not want to have the scenario where we go through every one of the records. We do not want that. Or even half of that. That would not be great either. Anything that involves the number of records in their entirety is not really ideal. Now, the biggest assumption that I'm going to be giving you, so this is the assumption I was alluding to, is that this hash function is good enough that it's capable theoretically of doing the following. Now, I will be presenting a practical scenario where it's capable of helping you get something like this, but I must stress that this is a theoretical assumption. So it may not necessarily be what your hash function actually does in the most truest sense, using the M word in the mayonnaise or mustard sense. So I must stress that this is just an assumption I'm going to make. So this always has to be taken carefully. It must spread keys uniformly, and I mean that in the statistical sense, uniformly across the entire table. So this is what I'm going to refer to as our uniformity assumption. So you can't just cook up any one hash function and it guarantees you something like this. There's only very specific kinds that are capable of doing this successfully. But even then, I'll be showing you one practical example of one that, while not perfect at it, will most certainly get you closer to something like this, at least in practice. And lastly, the third kind of big thing is collision resolution. So like, what do we do with the collisions? So how do we deal with these collision resolution? Like if we have a collision that happens, what do we do? That seems to be a really important thing we need to consider. And all three of these are things you have to consider when you're doing hashing. Hopefully that's clear, everybody. Is that these are all important elements of what makes an effective hashing technique. So each one may have their own pros, their own cons. So when we explore this topic, depending on how far along we get, it may make or break what we're doing.